This is They Create Worlds, episode 84, Time Shared.
If anybody wants to find me, I'll be in the last place you would look. In a place where people used to be, a land that's called reality, you'll find me there.
Welcome to They Create Worlds. I'm Jeffrey and I'm joined by my co-host, Alex.
Hello.
We will now delve back into the past.
The distant past.
The 1960s, where there was free love, drugs, rocks that roll, and video games that proliferated across the galaxy.
Or at least computer games. Now, obviously, we call all of them video games today. Technically speaking, most of these games would have not had graphics, though, because most people were interfacing with teletypes. But sure, video games across the galaxy.
Well, at least that's my hope.
So, a lot of people think that personal computing started with the Altair in 1975, and then moved on to the Trinity, which we've talked about before, TRS-80, Commodore PET, Apple II, and then from there on to Atari 8-bit, Commodore 64, IBM PC, and on into the future. That's what people think of as personal computing. IBM called it a personal computer.
It's your own computer that's here sitting at your desk doing your personal computing. You don't get to share with anyone else unless you have a sibling. Then you have to share with someone else. As far as the computer is concerned, there is only you, the user.
Exactly. But really, personal computing started a long time before that. Personal computing actually started in the 1960s, but it's not what someone who was using an IBM PC or a Commodore 64 circa 1985 would consider personal computing. Because instead of sitting in front of a monitor, you were usually sitting in front of a typewriter. And instead of sitting in front of a computer that was all yours, you were sitting in front of a computer that was being used by dozens, hundreds, thousands of people, or you might not have even been sitting in front of the computer at all. You could have been in a classroom in your high school, sitting in front of this typewriter, and the computer could have been hundreds of miles away at a major university.
That sounds a lot like having the internet where I have everything running on Google or Amazon and I'm telling it to do things.
You know, it's so funny. And I think we said this in one of our previous episodes. It doesn't matter. It was a long time ago.
We're bringing it into context now.
Exactly. When the microcomputer, as the personal computer was called in its earliest days to differentiate it from the mini computer, which already existed, there's a misconception that the mainframe and mini computer companies didn't get into that space because they didn't think that anyone would want to have their own computer. I mean, what would anyone figure out how to do in the home on a computer? I mean, it's ridiculous. Computers are just for scientists and researchers and airline reservations and banks. People wouldn't have anything to do on a computer in their home. But that's not really what the mindset was. Companies like IBM, which of course did eventually get in on the PC thing, but not right away, and DEC, which was the leading mini-computer company, and Hewlett-Packard, which was also a very big mini-computer company, Control Data Corporation, the supercomputer company. These companies saw that computing would be something useful in everyday life. But what they didn't see is why a person actually needed that computer in their house. They saw the future through networking and time sharing, a concept that we'll get into a little more detail here in a second, so that you had a dumb terminal in your home and you were connected to a computer someplace else. That's the part that they missed, that a person would actually want to have the computer itself in the house. But now, 30 years removed from the beginning, 35, 40 almost years removed from the beginning of the PC revolution, it's turning out that DEC and IBM and all of those companies may have actually been right. Because more and more of computing today is being done in the cloud. More and more stuff today is being stored remotely and being accessed from your computer at home. And your computer at home is obviously not a dumb terminal in the same sense. But we are much closer to that time-sharing model today than we were 20 years ago at the height of the PC revolution. So maybe they were right. They just didn't realize that in between, before we could get there, people would want a computer in the home. So I find that kind of interesting.
Personally, I think it's really more of a necessary hybrid of the two sort of concepts that is what is needed and what has really taken off.
Mm-hmm.
You need to have that personal computer, that's something that can actually do things, at least at some basic level. If you recall back to the 90s, if you're old like we are, you had computers in the home and you really enjoyed what you could do with it. Mostly that was type up my paper, maybe make some flowcharts, hand that into class, and then once that was done, then I can go play Wing Commander.
Right.
However, if you really think about it, back then, even though the computers that what we do and need to have stored locally is a few critical apps and games, you didn't need to have that external stuff going on. But now you have external things where, I can do this vast media entertainment by going to a myriad of places, Hulu, Netflix, YouTube, wherever, Pandora, and I can consume all of that media and have that really enjoyable. Or if my needs are really small, I can use something that's really, really weak compared to a computer even in the 90s, say a Chromebook.
Mm-hmm.
And all that's really doing is just running a web browser. That's all you need. That's your portal into everything that you need. And things have advanced well enough that you can do a lot of those things. Like I want to do word processing, Microsoft Office Online, Google Docs, probably one or two other places. There's my basic Word document things that I need, but your average user doesn't need all the big bells and whistles that the big desktop corporate person is going to need.
Right.
So it turns out that there's almost like if you're an enthusiast or a gamer, you need to have a better computer, but it's almost for like the mom and dad layperson student. You just need something like a Chromebook just to access those services. It just needs to be powerful enough in order to render the necessary things locally and enough storage to store whatever you're working on locally and then save off those copies off to whatever service you're interfacing with, which is very similar to what the old teletypes and remote terminals were, except those things were completely and utterly dependent upon the network that they were operated on.
Exactly.
If you started them up, you didn't have an offline version of whatever that you could do. There wasn't really much of a concept of being online. You had some sort of direct link. It was usually a dial-up link into whatever the mainframe or systems were.
Mm-hmm.
Even back then, it was something done on what's called an acoustic coupler, where you would actually take your handset that you would have for your phone, and this is, kids, you didn't have cell phones back then. This is where you had physical devices with completely separate handsets like you see in corporate offices, except more bulky. And they get set on this acoustic coupler, and then it makes sound in one end and listens on the other, just like you would with a phone, and goes back and forth. But really, the reason, as Alex said, this was all text-based is because that acoustic sound is going at 3,800 baud, which is 3,800 bits. That's with a B, small, ones and zeros.
Not bytes, people. Bits.
A second. That's astronomically slow. And it could drop down lower than that based on signal quality of the lines. So really, as we've said before, in at least a few other episodes, it really wasn't until we had the advent of true networks. And even today, I would argue we still do not have the kind of network infrastructure we need to properly support the system that we increasingly rely on.
Absolutely. That last mile is a real long mile.
It very much is. And you can see that in so many cases. It's like, yeah, in a lot of cities and urban centers, it's good most of the time. That's if you're lucky to have one or two options. You're really lucky if you have three. But most of the time, you only have one option. And I'm talking primarily from the state standpoint. I know in Europe, Japan,
South Korea.
South Korea, they have such superior networks to what we have here in the States. I just recall a person who was doing in this recent Games Done Quick. He was doing a run and happened to mention that he spends, because of where he lives, something like $400 a month just to have enough internet and bandwidth. That's
Jeez.
400 USD 2018 money.
That is insane.
Yeah, really insane. 4,800 a year just for internet. That's a big chunk of most people's rent.
Sure. Absolutely it is. I mean, we have a couple of problems. The U.S. government has not pushed creation of infrastructure in the way they probably should have. But in addition to that, I mean, one thing that's very different about the United States as opposed to Japan and even Europe is that the U.S. is big.
And a lot of people, especially not from the States, do not understand how big it is.
It gets really big out west.
Yeah, and there's a lot of rural space out there. I've heard people from Europe, Asia, and otherwise think, oh, I'll just fly into New York, I'll rent a car, I'll drive down to Miami, Florida, then I'll have a brief jaunt over to San Francisco. Anyone who is in the States just heard that and thought, so you're going to be spending at least half of your trip traveling?
Yeah.
For those who don't know, driving from New York to, say, Miami, which is near the top of the United States on the East Coast to near the bottom of the United States on the East Coast, that's generally a 2, maybe 3-day drive, spending probably about 8 to 12 hours driving a day. Driving from the East Coast to the West Coast, which is the Miami to San Francisco sort of run, you're looking at another 3-4 days of travel.
Yeah.
And that's not hitting traffic, not hitting a lot of other problems. So take that driving. I got to run a lot of cable, upgrade infrastructure, upgrade services to get that internet working. That requires a lot of money, a lot of investment. And at least in the States, this is getting a little bit off topic. We've went through this before, sort of with the electrification project, where we had electricity rolling out to the entire United States, but it wasn't hitting the rural areas because there's no money out there for it. And it usually took a governmental initiative in order to sort of get that going out there.
One of the real reasons that the U.S. ended up having so many very fine electrical engineering programs. I mean, today we think of electrical engineering as more often dealing with things like transistors and computer circuits and all of that kind of thing. But of course, electrical engineering as a discipline really started as electrical engineering, working with generators and transformers and power grids. And part of the reason why the United States ended up having so many fine electrical engineering schools is the United States had some really unique challenges it had to overcome in power generation and transmission in order to get power to all parts of the country.
All right. That's a bit long-winded and tangential there.
What, us go off topic? No.
But this is still germane because that's what you're kind of going into when we're talking about these terminals in the 60s. We think our internet's pretty okay, iffy now. In the 90s, it was That's the 90s. We're talking the 60s and 70s here. That's almost a 20 to 30 year gap difference there. You have people who don't even really understand how to even transmit that data reliably over phone connections or whatever it may be.
Right. So at this point, we should really back up and talk about this time sharing thing in a little more detail. So what is time sharing? To understand time sharing, you have to understand the way computers worked back in the day. Back in the 1950s and even into the 1960s, computers were big. They were really, really big.
Size of a house, big.
Some of the most powerful computers, like the SAGE systems used by the government for missile defense, air defense, were like half an acre of floor space taken up. You know, not solid, not all packed in, because you have to space stuff out for heating reasons and whatnot. But I mean, it took like half an acre of space to house a computer for the SAGE system. I mean, computers were huge. Because computers were huge, computers were also expensive. not just to purchase, but also to power and to keep cool, because they generated a heck of a lot of heat.
Not to mention operation, maintenance, so on and so forth.
Exactly. A computer was something that only the swankiest universities, only the richest of corporations, and only the most prestigious of the government think tanks would have to help them in their work. Even those organizations wouldn't have that many of them. So if you were at a prestigious university like MIT that was even lucky to have a computer in the first place, not all universities did, you were probably talking about one computer to serve your entire population of professors, students, and researchers that needed to do computing. So how do you most efficiently use a single computer that can only handle a single operation at a time to serve that many needs? And the answer is batch processing. Tell the kids about batch processing, Jeff.
Sure. The simplest version of this would be a stack of punch cards.
Mm-hmm.
You take those punch cards, you put them in the input tray, and the computer would load each one, do whatever math jigger-pokery it was doing, spit them out the output tray, and then have some sort of secondary output ticker tape, printy thing, maybe even another punch card that it just put results on. So you had an input, output as far as what you're putting into it and what's coming out of it, and a sort of results thing going on. As long as you kept that input hopper full, cleared out the excess already read ones, and made sure that the pile of ticker tape on the floor didn't jam up anywhere, all was good. A lot of the operators just sort of sat there with going, all right, you're still churning, still churning, still churning, still churning. Oh, it looks like Bob mispunched this thing, which then caused that over there. So I'm going to take this program, take it out, set it aside, and write bad boy, and send that back to that person. Okay, let's hit the reset button. All right, let's restart the batch. Okay, churning and churning.
Exactly, and on and on. And so, of course, they weren't just doing one person's program at a time. They'd have a bunch of people that had submitted programs, and then they would feed them through sequentially on the cards. The way programming worked is you would punch out your program on these cards, and then you would take your stack of cards down to the computer center and hand it over to the operator. The operator would put that in the queue of jobs that would be done on that computer, and they would feed through jobs as they could as they got done. And so 2-3 days, or maybe even a week later, you would come back and you would discover if your program ran or not. Because if you had any errors in it, they'd be, well, here's the result that's spit out. We have an error someplace. And so then you'd have to comb through all your cards again, see where that error was, and then go to the back of the line again to submit your program again and wait however long you needed to wait.
As you can imagine, this was an arduous process, and because of the turnaround time being so long, you only ran programs you really, really, really couldn't run yourself.
Exactly.
It was like, okay, I could crunch the numbers on this and I could get it done in a day. I'll do it. I can crunch the numbers on this and I'll get it done in a month. The computer does it.
Exactly. So, a very inefficient process, but the only way to efficiently, I just called it inefficient, but in the context of the times, the only way to efficiently deal with submitting computer programs in that kind of environment. So at MIT, they had a little computer project that I think we've touched on in the podcast before, but if not, I've certainly touched on it in my blog. They had a computer called the Whirlwind, an experimental computer. It was the world's first real-time computer. And I know we've talked about this before, how the Whirlwind was the first time where you could tell it to do something, and it would immediately do that thing, within whatever the lag is. But the lag is so tiny that it feels like it's doing what you're doing in real time. But the Whirlwind was not meant to be a quote-unquote real-time computer in the way we think of real-time computers today. It was built to be a command and control system for a nationwide air defense network. It had actually started as a flight trainer. That didn't work. Then the Soviets detonated an atomic bomb, and we realized that we needed a defense system to alert ourselves to Soviet bombers. This is before ICBMs, before missiles. So specifically to make sure bombers aren't flying over Alaska from Russia to come and bomb us. We needed a nationwide air defense system. So Whirlwind as a real-time computer was a command and control system. It wasn't a computer where you were going to sit around and play Galaga on it.
No.
Nevertheless, it was real time, and people did program on it. And there were MIT graduate students that programmed on it who really enjoyed that interactive environment. And it's hard to overstate how influential Whirlwind was in the creation of video games, because we talked about this in the context of the Space War episode. The reason that Jack Dennis recruited these people from the Tech Model Railroad Club to program on the machine, you know, the group of staff members and students that ended up between them creating Space War, is because he wanted student experimentation and he had programmed on the Whirlwind. So you can trace a direct line from Whirlwind to Space War and from Space War to the rest of the video game industry. But you can also trace a direct line from Whirlwind to the concept of networked computing as it existed in that time period. Because some of these same guys, not Jack Dennis, but some other guys, most notably a guy named Herb Tiger and another guy named Fernando Corbato, had also programmed on the Whirlwind. And they were like, this is great. We tell the computer to do something and it does it. It's like, why can't we do that with our other computers, with our big IBM machine in the computer center? Because by this point, mid-50s, MIT had inaugurated a computer center with an IBM mainframe in it. And the answer to that is not just the real-time thing. I mean, you could have theoretically, it would take some overhauling, but you could theoretically have turned one of those hulking mainframes, one of those IBM machines, into a real-time computer. You'd have needed to add some specialized hardware to it, but it's just a matter of having fast enough transistors and fast enough memory that it can process commands so quickly, and you need some shift registers and some parallel processing as well, but it processes commands fast enough that it happens in real time.
Keep in mind, computers today, at least from that standpoint, they don't really do anything real time. They do one thing. That's it. One. Okay, but Jeff, my computer is playing me music. I'm watching my YouTube video and playing StarCraft 2 at the same time while listening to you. A, you have an amazing ability to differentiate sound. And B, the computer is lying to you.
Yes.
What we have and what the Whirlwind system sort of started to introduce is a way of efficiently shifting between the computer doing things all at once and properly using resources. CPUs are fast. Insanely fast. Even back then, extremely fast. But it's slow. No, fast. You see, the computer goes really, really quickly, and a lot of the time it's going, hard drive.
Yes.
Oh, great, thank you. Okay, now I need something from RAM. Paging Dr. RAM. Dr. RAM, please come to the CPU. Okay, great. User. Here, user. As you can see from my demonstration there is the CPU is, in the old days where it's doing those batch processing thing, is sitting there doing nothing.
Right, exactly.
Nothing at all. That's bad. We started doing a lot of advanced things. You have different parallel execution lines. You have interrupt requests. So this is why back in the day when you had IRQs and what we called lovingly IRQ hell, the reason we had that is because we're trying to use things more efficiently. Instead of the CPU sitting around tapping its foot going, all right, waiting on that keyboard. Waiting on the keyboard. We go, all right, I am running this. I'm processing this, and then bing! I see in my inbox I have something from the hard drive. Fantastic. Which program that I'm working on is that for? Oh, okay, great, fantastic. We'll just hand that off. Let's do a little processing here. Bing! Hello, RAM. You have provided me with that information. Fantastic. And bing! Oh, the user has hit Control-Alt-Delete. Panic!
Right.
So you see there, you have interrupt coming in. It's a lot more complex than I am sort of simplifying here.
Of course.
I will, of course, throw for anyone who's interested in, I will try to look up some good YouTube videos. I may or may not be successful on this. That sort of goes more into depth on how you had this evolution of just the CPU sitting around waiting and twiddling its thumb to, hey, we got all this interrupt stuff going on. We have sort of like this parallel processing thing going on, all sorts of crazy things, sort of like this offloading stuff of going, okay, this really complex thing, I'm going to hand that off to the video card, this complex sound thing, that's going off to the sound card, and then they'll alert the CPU through sort of like command and control going, all right, we're done with that, here, send this off somewhere.
Exactly, because even those old computers had CPUs. Today, when we think CPU, we think a microchip. And it's like, well, really, the fact that it's a microprocessor is incidental to it being a CPU. You can have a CPU without a microprocessor. It's just it's spread out across all sorts of crazy hardware. It's spread all across a circuit board instead of being one nice little microchip like we have them today. So even back in the 50s and 60s, they had CPUs.
Right, and the CPU did everything. It did the video, it did the sound, it did I.O. Today, we have our CPU offloads all that. You have a video card. All that is just a CPU whose job is, I'm just doing the video, man. The sound card, I'm just doing sound. Those other little chips you see on the motherboard, those are things that go, I'm handling just the I.O. with the hard drive. I'm handling the I.O. and interface with some of the add-in cards. I'm handling the I.O. with this, that, or the other thing, your Wi-Fi signal, whatever's integrated on the system.
And then they all board Mr. Bus so that they can all go talk to Mr. CPU.
Right. And so just how we got things faster and faster and faster is by a combination of offloading and all that. Again, I will throw in some more stuff into the show notes for those who are interested.
Absolutely. So the technology existed to do a real-time computer, obviously, because Whirlwind was a real-time computer. It was cutting-edge technology. It was just coming in, but the technology did exist. But just being real-time wouldn't solve the problem. Because, okay, so great, I can type something into my IBM computer and it'll happen right away. Huzzah. Well, I still only have one IBM computer. That IBM computer can still only handle one user. So you haven't solved anything. Doing a one-on-one real-time deal with the mainframes of the time when computing resources were so scarce lost you time compared to batch processing. So there was no point in making it real-time.
So it's sort of like in our modern parlance, it was a single user system.
Right.
You signed in as whoever the single user was, and the CPU is just talking to you and going on and so forth. Nearly everything we have now is a multi-user operating system.
Right.
Where more than one user can log into it. Even Windows. Usually you have to pay Microsoft more or do some interesting jiggery-pokery. And you can have multiple people sign into any operating system and do whatever they want.
Mm-hmm. But there were a group of people, and John McCarthy, the AI pioneer at MIT, he was at MIT at this time, he didn't start there.
Not the Beatles.
Yes. Was one of the first people, not the very first, but one of the first people to be like, okay, wait a minute. When I am sitting at a computer, if I were to sit at a hypothetical real-time computer and be interacting with that computer in real time, that computer really is not working for me all the time for the exact same reasons you just articulated, because the computer is waiting for this to get done over here, this to get done over there. So all of the cycles aren't being used. Plus,
even as you're typing,
right,
the amount of time between you hitting, even you could be a fast typer. Compared to the computer's going, that's like eons as far as the computer's going in between each letter.
Plus, there's just the periods when you finished running a calculation and you're running through and looking at the results, and you're literally doing nothing with the computer because you're just sitting there reading what's on the tape, or if you're really fortunate, what's on the screen. Weren't many screens back then. So it's like completely idle. It's not even doing anything. So it's like we have all of this computing time. All we have to do is come up with a system that allows the computer to switch between users rapidly, and then throw enough memory into that computer that even as it is starting to slice little slivers of that memory off to do this little thing for this guy, this little thing for that guy, this little thing for that guy, each individual user still has enough memory dedicated to what they're doing that the whole thing doesn't slow down and fall apart. And we can have lots and lots of people using this computer at the same time.
Not to mention a little bit of extra RAM for just the overhead and management of all of that.
Exactly.
And thus, you get Unix.
Yeah. Well, you do. That's skipping ahead in the story a little bit, but Unix came out of time sharing. It very much did. So this is where this idea of time sharing comes from. And it literally means you are sharing computer time. And when we say computer time, what we're talking about is cycles. We are sharing computer cycles because we are not actually using every single cycle per minute that computer is capable of. So the time that we are not using in our calculation is being sent over to the other guy, and he is sharing our computer time.
Yeah, you remember how your computer's like 2.4 gigahertz or something like that?
Right.
Well, back in those days, we had things like 386s and 286s and 186s and...
Well, 8088s.
8088s.
Yeah.
One of our first computers was a 386, and it was deprecated by the 486. It went at a whopping 60 megahertz.
Mega.
With an M. So, you know how you have your 1.7, 2.4, 3.6 gigahertz processor now? No, 60 megahertz. So that's, let's say 60 million a second for sake of argument here. And it only takes, say, 5 hertz to register a keystroke.
Mm-hmm.
There's all that extra time. There's so much little slices, all those little slices. And those are all those little cycles. Matter of just how many active things can we shove in there to make the whole thing work.
Exactly. And so you're throwing away cycles. And that's what people like Corbato and McCarthy at MIT realized, is you're throwing away cycles. So let other people use those cycles. Connect multiple interfaces, which was usually a typewriter or a teletype in this day, into a single computer. Let everyone do their thing at once and have a monitoring program that is able to balance what everyone's using and switch between everybody's time. This is the beginning of the operating system, by the way. You did not need a real operating system on a batch processing computer because it was literally just doing one thing at a time. That doesn't really take a brain to do one thing at a time. But once you're talking about, okay, I have to have all of these peripheral devices, teletypes, plugged into this machine. I have to have switching between all of these different users. That's why you get operating systems.
Yep.
And even on, like we said, even on your single user computers, modern single user computers, those computers are really still doing a bunch of different things simultaneously, even if they're doing it just for one person instead of many. And again, that's one of the big parts. It's not the only parts, but one of the big parts of an operating system is memory management, because you're parceling out memory to all of these different processes at the same time.
And then we have the operating system for operating systems, which is virtualization, which is why we have this sort of move to virtualize everything, is because we have hardware that's so fast, so capable. Let's use it efficiently. So we'll put this hypervisor here and then throw a bunch of virtual machines on it that only need so much. It's taking how things used to be at a user and then system level and doing it from a system level to really super mega system hardware that can technically run 7 operating systems at once or more.
Sure. Exactly, because the computers just keep getting faster and faster. That Moore's Law, we keep almost coming up to it, but that Moore's Law keeps going on. We double every 18 months. So what does this mean in terms of time sharing? Well, what it means is some guys at MIT got together and they created a prototype system called the Compatible Time Sharing System, the CTSS. It ran on their IBM big hulking mainframe, 7090 computer. And in its initial form, obviously it kept evolving, it was one computer, 3 teletypes or typewriters hooked into that computer, plus, because it's still got the 7090's batch processing interface, that computer can also still batch process. So you can have 3 users using the computer simultaneously, and you could have a 4th process going on in the background that was kind of the batch process that would pick up when any of those other 3 weren't doing anything. So you could have 3 users and 4 processes. I mean, people are using more processes. In processes in this case, I mean programs running, not literal processes, going on at the same time on a single computer. And this was revolutionary because what this meant is that you could open up computing to way more people. Those people did not even need to be in the room, same room as the computer, because we already had modems. AT&T invented the modem in the 1950s. The Sage air defense system that I talked about was using modems in the 50s. So we had modems already. That part was solved separate to time sharing. Now, with the time sharing, you don't even have to be in the same room as the computer. And you can interact with the computer in something approaching real time. It's very much more like what we do on even our home computers today, where you're sitting in front of a keyboard, even if you're not sitting in front of a monitor yet, and you're typing and stuff's happening in real time. And you get the illusion that you're the only one using the computer. I mean, during peak use, or if somebody's running a particularly complex program, you might notice that sometimes the computer is way slower than it is other times. But you're given the illusion of a single user experience. It's personal computing. It's just not a personal computer. So there's a second thread that we have to bring in here because, okay, great, more people can use the computers. Well, there still aren't that many computers out there, right? And computers are still primarily for big, important work. So how do we get from there to lots and lots of people getting to have access to computers? Well, we kind of get there in a way through the space race and through Sputnik and everything. It is hard to overstate how much Sputnik scared the living hell out of everyone who was an important decision maker in the United States. Sputnik, of course, was the first man-made object launched into space, launched by the Soviets, 1957. By the Soviets, not by the U.S. Today, they're launching a satellite into space. Tomorrow, they're raining nuclear missiles from space down onto the American heartland. And we are powerless to stop it because they are way ahead of us. We have not gotten anywhere near here in our space program. This was scary stuff in Cold War America. There were a lot of things that the government did to try to counter that. But one of those was a real emphasis on improving technical education and technical aptitude in schools in the United States. And a big part of that was having the National Science Foundation give out grants to anybody, big grants, big money, to anybody that was running projects that could have something to do with improving American technical aptitude. So this is a big part. There's money coming available, grants coming available that are going to allow some of these schools, colleges and high schools even, to have the resources they need to purchase these expensive machines. Then you also have kind of the idea of computer-aided instruction beginning to percolate for the first time. You have rural school districts in the United States that are really falling behind urban school districts. Remember, even in the early 20th century, you had a lot of kids in rural areas that they did not go beyond the 8th grade in their education. You had a lot of one-room schoolhouses. You still had one instructor that was teaching all the grades and was supposed to know enough to impart the knowledge needed by kids of all ages. So you had a rural school system that was pretty poor in the United States. And over the course of the early 20th century, a lot of these rural districts were trying to improve. They were modeling themselves on the bigger school districts in urban America. And that worked for a while. Some of these school districts were doing okay, but the problem is learning continues to get more complicated. The things people need to know continue to get more complicated, and subjects continue to become more specialized. And as subjects become more specialized, you need more specialists to teach them. You don't just need a science teacher. You need your biology, your chemistry, and your physics teacher. Then really you need multiples of those then, and it just snowballs. You need your teacher that's really good at geometry and your teacher that's really good at algebra. And specialization, specialization, specialization. So urban schools are getting bigger. They're getting bigger staffs because they're specializing more. Rural districts can't keep up with that. Even today, they have problems keeping up with that. They certainly had problems keeping up with that in this period we're talking about, the 1950s, 1960s. So there was a real crisis in rural schooling. One of the responses to this was to come up with the idea of intermediate school districts. And what an intermediate school district basically was is you take several school districts and you give them the authority to combine together for certain functions. They're still independent school districts with their own resources, but they have the authorization to, for certain kinds of projects, come together, pool their money, and do a big joint purchase or a big joint project of some kind. Another thing that people were looking at was the emergence of the computer. If we can replace teachers, and, replace, I mean, some people were thinking augment, but others were thinking replace teachers with computers that the students can interact with and do all of their schooling with, then we've negated that advantage that the urban school districts have, because a computer is a computer. You don't have good teachers and bad teachers, and to get the good teachers, you have to pay them more money to get them to come. I mean, yeah, obviously there are computers of varying power and everything, but I mean, at the end of the day, a computer is a computer is a computer. So if you get an intermediate school district or even an entire state to invest in uniform computer hardware and uniform computer software across all of the districts, then you have, in theory, a more sustainable and more expert education apparatus within your rural school district. I mean, does that kind of make sense what their logic was?
Yeah, it makes sense, and it's actually something that was prevalent in the minds of the people at the time. Isaac Asimov actually wrote a short story where he depicted a future in which your students were in a classroom, just like they are now. Like, there is no teacher. There is just a central computer interface that's there that dictates homework, dictates lessons, dictates this, dictates that. Really impersonal from our standpoint, but in the way it's portrayed, at least in that short story, is this is a very viable and sought-after thing. And I think that very much speaks to the attitude from a societal standpoint at that time, where people were seeing these computers and going, yeah, I can see the capability of that computer teaching my student, my kids, the basics of whatever that is. And from that standpoint, yeah, I can sort of see that. Math is math is math. I don't need to have someone who has a doctorate in advanced rocketry teach elementary school 1 + 1, addition, subtraction, long division, multiplication. I can just have a program that does that.
Precisely. So there was this real push to bring computers into the classroom, and time sharing became an important part of this process because it allowed for a school district or an intermediate school district, a bigger grouping, to buy 1, 2, 3 computers, but then spread that computing love throughout an entire school district through remote teletypes. The very first big kind of successful time-sharing network was actually started at Dartmouth, an Ivy League school. Now, Dartmouth, like many of the colleges in New England, actually used the MIT Computation Center for its computing needs. So if you were a Dartmouth professor and you needed to go run a computer program, you would take the train from New Hampshire down to Boston and go to the computer center and give them your programs. And if it was something completed same day, maybe you'd wait around, or maybe you'd come back next week, and then you'd be able to take your program back to Dartmouth. Well, I mean, this is an even more inefficient use of batch processing than the actual MIT professors using batch processing, because you're adding the whole other step of you have to take a train ride even to just use your computer. And there was a professor at Dartmouth, John Kameny, Hungarian, brilliant. He had worked at Los Alamos on the Manhattan Project. He had been in graduate school. He had been Albert Einstein's personal research assistant at Princeton. Brilliant guy. He realized that this just wouldn't work anymore. If Dartmouth was going to continue attracting good mathematics professors and good mathematics students, they were going to need to have their own computer. He was able to set aside a little bit of the money that was going into the construction of a new mathematics building for the university, get a little of that set aside to buy a little computer, literally for the time little. We wouldn't call it little today, but they would then. A little computer called the LGP-30. It was a tube computer. It was pretty basic. It was nowhere near the same as the hulking mainframes, but it was a computer. And before, Dartmouth hadn't had a computer. It was a little more interactive because it was a smaller computer. It was a little more interactive than your big hulking mainframe. So Kamini and his students did a lot of, experimentation and had a lot of fun kind of fooling around with it in addition to it doing, official university work. And it was kind of through this interaction that Kamini really began to think that, this computer stuff is getting more and more advanced. The ways that people can interact with a computer are getting more and more sophisticated. And I can see a future where everyone is going to need to be able to use a computer. And he doesn't just mean use a computer as we do today in terms of I'm sitting at my keyboard, I'm typing the email, all of that stuff. No, I mean, he means actually being able to have to do some basic programming in their everyday lives as well, some rudimentary programming. And he became very much a proponent of we have to introduce this into the curriculum. But again, he can't do that with what they have right now, the LGP-30. It's one computer. It's relatively weak computer. You can't teach all of Dartmouth how to program or how to use a computer on that machine. Well, he had a protege, a professor, another professor in the mathematics department named Thomas Kurtz. Thomas Kurtz came to very much believe in the same vision that Kamini had of this computing for everybody. Everybody learn computers because it's going to be an important part of daily life. And Kurtz learned about time sharing from MIT, these early experiments that are being done on the CTSS by people like Fernando Corbato. And so he realizes that time sharing is the way that you do this. You can create a computer network at Dartmouth that multiple students can interact with at the same time. And that way you can provide computing to the entire school. And he tells Kamini about this, and Kamini thinks that's great. And so they do that, and they start building the Dartmouth time-sharing system, the DTSS. There's just one problem. As I said, they believed that everybody was going to have to program at least a little bit on a computer in the future. But if you wanted to program on a computer in 1963, 1964, when they're putting this all together, you have basically three options. You have machine code, which is literally the exact patterns of ones and zeros that the computer processor processes.
Opcode 1725. Opcode 376. Opcode 4522. Opcode 1637.
Then you had assembler, which was still basically machine language, but these commands were assembled into something a little more comprehensible to a human, but it's still basically machine language. It's still telling it to do one little teeny tiny thing at a time.
Load register 1 with the contents of keyboard.
Yeah.
Load register 2 with the contents from memory sector R2. Please add those two values together and store them in registry number 3. Then take result registry 3 and print to output device 7A.
Yes. Or you had the very early high-level programming languages. There were a couple, and they were called high-level as opposed to low-level. So machine language and assembly are low-level. They're called low-level because you're directly on the metal. You're directly on the processor. So it is different for every computer configuration, every processor configuration you have, because each processor has different pins, different IOs, different calls. And so if you create something in machine language on one computer, you cannot use it on another computer that doesn't have the exact same setup, because it's going to be calling to all the wrong places and everything's going to be confused. A high-level language is an interpreted language. And what this means is there is an interpreter program that has interpreted the commands that you have put in into the specific language of the processor that you are dealing with. And therefore, you can use a high-level language on many different computers.
And thus did Bob take the numbers 3 and 5 add it in together and put it out on the monitor. Okay, computer, go handle that. All right. If he says Bob, he means that it needs to be that. Okay? And add means I have to take these two registers, so on and so forth. All that stuff I said earlier.
Exactly. And so you do have to create a different interpreter for each type of specific system you're using your high-level language on. But as long as an interpreter exists for the specific machine language that you're working with, you're going to be fine. You can use those same high-level commands on any machine that it's been interpreted for.
And that's where you get into the whole compiler and object linking and all that other stuff you may have heard of before if you take any kind of computer-based class. You have a compiler that's designed for a certain hardware architecture. Since most everything is x86 based, primarily most compilers compile to that. But say for ARM processors, you need to actually have an interpreter that will take your C code, your Java code, your whatever code, and convert it into what ARM expects and what the x86 expects. Back in the day, you used to have a special compiler for Macintosh systems because they had a completely different chipset before they adopted the x86 architecture.
Right. The first high-level languages came into existence in the mid-1950s. Fortran was the very first one. COBOL and ALGOL were also very early. But these languages were either made by engineers or mathematicians for use in their own work. And because they were engineers in the case of Fortran or mathematicians in the case of like COBOL, those programming languages thought like an engineer and thought like a mathematician. So you had to have a fairly good grounding in engineering or mathematics to make any kind of sense as to how those languages work. They were technical languages.
And they're still used today in ancient systems, and the people that still know how to program in those are kind of starting to become a rarity.
Right. They were still, even though they were general purpose languages, they were highly specialized just by the nature of the people that had created them and the people that were working with them. So you might be able to get your brighter mathematics students to program on your time-sharing system using Fortran. And maybe you can simplify Fortran some, create a simplified version of it that even your less bright mathematics or engineering students would be able to make sense of. You're probably never going to get the majority of your humanities students to be able to do much of anything in Fortran because they would have to dedicate so much study to it. It's not that they may not be capable intellectually. It's just that kind of has to become your entire focus of study, and those people aren't going to school to learn how to be engineers. They're learning how to be historians or English teachers or something. So you could not use the existing high-level languages if you were pushing a message of computer use for everybody. It just wasn't going to happen. Well, Kamini and his students, because I told you that they had been doing some, just experimentation on the LGB30. I mean, just like Jack Dennis, who encouraged the students at MIT to experiment and do what they wanted because he thought that kind of freewheeling experimentation was just as valuable as real research in terms of figuring out what a computer can do and how best to advance computer science, which was barely even a concept then, computer science. So too did Kamini think that this kind of experimentation was great. So he had been experimenting with students on this LGP30, and they created something called DOPE. It was an acronym. I forget off the top of my head what it stood for. It's not important. But they created a really simple language called DOPE. That's why the acronym was DOPE, because it was so simple, that practically anybody could use. Now, it was a limited language. You couldn't really do any real programming with it. But the important thing is that it was very natural language and was very easy to understand so that you could play around with it. But it wasn't really powerful enough to do anything with. But because they had done the DOPE thing, Kamini thought, we can make a language for our computer system that A, uses natural language commands wherever possible, and B, is structured in such a way that you can do very simple routine tasks with just a few simple commands, just a couple of lines of code very easily. And then once you grasp kind of how it works, then you can start introducing complexity on top of that, which means you have a nice, gentle on-ramp into the language. So he came up with a little language called the Beginner's All-Purpose Symbolic Instruction Code.
That sounds pretty basic to me.
Precisely. What does that spell, folks? Basic.
Which is still used today.
It really is. Obviously, it's gone through many permutations, and Dartmouth Basic is not the same basic that people use today.
Primarily the basic that is used today is basic.net.
Mm-hmm. This is basic. This is the same basic. This was the invention of basic at Dartmouth, either in late 63, early 64, somewhere in that time period, solely because these two professors had a vision of everybody using computers. And they were wrong, of course. That's no fault to them. This was kind of the belief at the time, because people hadn't really cottoned on to the idea that computers could be made so simple that anyone could just start clicking on things and things would start happening, and you wouldn't have to know anything about how the underlying system works to be able to get it to work for you. They hadn't seen that world. This was a period of time when a computer programmer and a computer user were the same person.
Inseparable.
Right. They ended up being wrong that everybody was going to need to know some degree of programming. They were correct that everyone was going to be using computers. They were wrong that using a computer meant that you also had to be at least a rudimentary programmer. But the important thing is because they did think that, they came up with the simplest language they could think of.
Yay, basic.
Right. And, just about anyone who grew up, in a certain period of time, at least knew the basic commands for printing their own name over and over again on their Commodore 64.
I may have forgotten it by now, but yeah.
Right. Because, even when we were kids, you didn't program in DOS to use DOS, but you had to give DOS commands in order to get it to do anything.
People of our generation are very familiar with modifying autoexec.bat in order to free up enough memory to play TIE Fighter.
Well, sure, but even giving simple commands to change disk drives or show the directory structure of the drive, even that kind of thing, that's not...
Running edit.
Right. That's not programming because you're not creating something new, but it is having to know how to give the computer commands. In its most simple rudimentary form, that's what programming is telling a computer what to do.
It's just funny. Today you start up a computer, you have this intuitive user interface where people sat down and said, okay, I need to have something where grandma can look at this, and engineer can look at this, and a child can look at this, and figure out fairly simply what to do in order to do what they want to do. I turn on an Apple II, and I have a cursor. Have at it, kids. Have at it. What am I supposed to do?
Computer. Hello, computer.
Use the keyboard.
How quaint.
Bonus points if you get the reference.
Exactly. So even though this didn't end up being necessary, what it did is it did open up computer programming to a wide array of people. You did not have to be a mathematician. You did not have to be an engineer. You didn't even have to be a college student. You could be a high school student or a junior high student, an ordinary one. We're not talking about the geniuses. There's always those geniuses that started coding in machine language when they were 3 and can keep all the hex commands in their head for simpler processors, not for like modern Pentiums, but for like 8-bit processors, could keep all the opcodes just in their head. You always have that genius, but we're not talking about the geniuses. We're talking about the ordinary Joe Schmo down the street can, with just a little bit of application, learn how to program. Program great, big, huge works? No, but program something. So we're opening up computer use and we're opening up program creation outside of a small circle of experts into a large group of laymen. And that's what you needed. The reason that you didn't really have computer games before the 1960s, other than a very small number of demonstration programs and AI research routines and military simulations, is that you did not have computers that could accept enough people at one time to make that an economical use of your machine. And even if you did have a computer that, against all odds, you could actually efficiently use for this kind of thing, you had very few people that could actually program on these computers, and most of them were people that were learning how to program professionally. They weren't learning casually or for fun. So they were, of course, focusing all of their work on doing serious research.
So now we have time sharing working well. We have BASIC, which then allows just about anyone to use that time shared system well.
Exactly. And then the Dartmouth system, what they do, because, I mean, Kamini and Kurtz, they're real genius. They weren't the first ones to do time sharing. They learned about time sharing from MIT, which were the first ones to do it. And MIT is continuing to work on time sharing throughout this entire period. But what the genius of Kamini and Kurtz was, is that they believed everybody needed to learn it. They introduced it into all the basic math courses at Dartmouth. And Dartmouth's an Ivy League school. I mean, just about everybody had to take at least the basic math course, even if they were going on to be history people or English people or psychology people or whatever. They had to take the basic math courses. And so they introduced basic programming into the introductory math courses. You know, just taught you a few commands, had like 2 or 3 weeks of instruction on basic, and then you had to create a program. It didn't have to be elaborate. But that was the hook, right? If you really didn't care about knowing more than that, you didn't have to. You were done. You would never see basic again. But if having control of that machine in that way caught your imagination, then there was a whole world open up to you now, because you had the Dartmouth time sharing system. You could go to the Kiewit Computer Center and you could sign up for time on one of the terminals. They started with 30 and it greatly expanded over time. I should say that fall 1964 is when they first started using this. They completed it in early 1964 and it entered the curriculum in late 1964. So it started with 30 terminals and it expanded hugely from there. So you could go down and you could just program. And you see, Kamini and Kurtz, just like Jack Dennis at MIT, there's a lot of parallels here between the Dartmouth crowd and the space war crowd. Just like Jack Dennis at MIT, Kamini and Kurtz really believed that all experimenting on computers is good, because all work on computers makes you more familiar with computers and makes you understand computers better. And because their whole goal was not to use computers just for research, but to empower individuals to use computers in their everyday lives, they didn't care if it was a school project. They didn't care if it was research. They were just like, here is the resource. If you've become interested in this, go program. That is a fundamental change. And even though it's similar to the MIT Tech Model Railroad Club situation, time sharing is the difference. Yes, you had all of these kids clustered around the TX0 and then later the PDP-1, and they were all clustered around playing Space War. But they weren't time sharing. Later on, the PDP-1 would be time shared, but we're just talking out here. So it's still just one computer, one location, one small group of people. But now you have all the Dartmouth people, and then because they really believed that everyone would have to use computers, they decided we should not stop here. It should not just be in the college. We need high school students, junior high school students, starting to learn how to program. And now that we have time sharing, that's possible because we have the computers here at Dartmouth. These schools don't need to get computers. All we need to do is hook them up with a teletype and hook them up with a phone line. This is all modems. This is all over the phone lines. Hook them up with a phone line direct back to our computer, and then they can do this stuff remotely at the schools. And you see the NSF is giving out grants. This is where we bring the NSF back in. They want technical education to improve in the country because we are losing the space race with the Russians. So here's a lot of money to go do this, to go do these phone lines, to go do these connections, to pay for the long distance costs that you're incurring by having these remote lines. It's government money that's making this happen.
Pay for the terminals that need to go into these schools. Pay for the expanded computer infrastructure in order to support the new users.
Exactly. It's all coming together. And so it goes into high schools. It goes into junior high schools. And again, it's about the joy of programming. It's about getting kids interested in programming. So of course, at the high school level, we're not doing research. It's not a university. at the high school level, it's just, let's get these kids comfortable programming. Let's get them interested in programming. So, of course, they can create games. No one's going to stop them unless they're, the biggest humbugs in the world. No one's going to stop them from making games. And in fact, Khomeini really thought that games were a fabulous idea. And this is another thing that set Dartmouth time-sharing system apart from some others. On a lot of early computer networks, the games naturally crept in because people like playing.
Gaming is fun.
Exactly. But some of the more strictly educational time-sharing systems, because as we're going to see as we develop this, a lot of other time-sharing systems start popping up specifically to facilitate computer education initiatives. A lot of them are like, well, we're really here to do computer-assisted instruction. We're really here to do learning. So games are not the reason that we have computers, so you should not be wasting time doing games. But Khomeini, he was like, my job is to get people comfortable with computers. My job is to get people to use computers in their everyday life, because in the future they're going to need to use them in their everyday life. Games are a great ambassador. It places you in something that is somewhat familiar, a scenario that you are familiar with. It's fun. It's a gateway into computing. So he encouraged games on the Dartmouth time-sharing system. There were several football games made on the system because football was pretty popular at Dartmouth. There were basketball games made. There were baseball games made, checkers games, chess games. All of these kind of rudimentary kind of simulations were made because A, they're fun, and B, yay, it's fun. So let's have people have fun on the computers because we want everybody to feel like they can use a computer. The Dartmouth time-sharing system is the key advance to time-sharing becoming more generally used. It was the first commercially successful time-sharing system. MIT had been doing their experiments, but they never could get their act together. They spent a long time working on their Project Mac, which was their time-sharing project, and working on the Multics operating system for that time-sharing network, and they just couldn't ever get it to run very well. Large-scale time-sharing, they just couldn't figure out. That was a combined project with Bell Labs. And then one of the guys from Bell Labs went home went back to Bell Labs, I don't mean literally his house, and started playing around with time-sharing on his own and ended up creating his own operating system. And because he had been working at MIT on Multics, which was an acronym for Multiplexed Information and Computer Services. And he was creating something that, in a way, felt a little simpler than Multics. He came up with the pun of calling his the Uniplexed instead of Multiplexed Information and Computing Service. And if you create an acronym for that...
Unix.
Exactly. So this is all going on that side of things, but Unix is still several years in the future. Multics and Project Mac are falling apart. DTSS is successful. It's commercially successful. It's getting out there. GE provided the computers for DTSS. General Electric did. And the reason for that is almost accidental. General Electric was one of the so-called seven dwarfs that was trying to compete with IBM in the mainframe space and was failing pretty miserably. But they happened to have a particular computer model that was particularly good at handling inputs from multiple systems. So they actually partnered with GE because they could use a regular GE mainframe plus this other computer that was good at handling multiple inputs in tandem to create a better time-sharing system than they felt they could get out of IBM hardware or control data hardware or something like that. So GE ends up becoming Mr. Time-Sharing as a result of this. Project Mac then ends up using GE computers as well, and GE starts creating computers that are specifically geared towards time-sharing. Then they start setting up commercial time-sharing centers. They actually start creating centers all over the country that have these GE computers in them that you can then lease terminals and lease time to use their system. So now time-sharing is spreading even beyond Dartmouth and some of this into the commercial world and also into more of the school world. When GE is successful with this, other commercial companies start up doing the same thing. Then the mini computer companies notice what's going on. The early time sharing is all on mainframes, which means, if you're buying the computer, you have to buy one really super duper expensive computer. And then you're parceling out the memory and everything through time sharing through the terminals. But that initial purchase is still a huge purchase. Well, the mini computer companies start seeing the success that GE and Dartmouth and whatnot are having with time sharing. And then they're like, you know what? We can time share our mini computers, which are much cheaper than the mainframes, and then offer these to schools. Because again, the buzz is kind of like, this is going to be great for education. We need to get in the schools. So PDP retrofits its PDP-8, which at this point is their main mini computer. They retrofit that into a time-sharing service and specifically target schools. They call them edu systems, DEC edu systems, but it's basically a PDP-8 computer with some just slightly different configurations that they market to schools. So then smaller intermediate school districts or school districts that don't really have the money to buy a big mainframe can buy a couple of mini computers and still time shared, still hooking up remote terminals, but it allows even smaller entities to get involved with the time sharing. And then HP, mini computer company, comes in and does the same thing. So now, by the very end of the 1960s, very beginning of the 1970s, you have hundreds, thousands of school children that are now able to, at school, do computing.
And this isn't just college students. We're talking high school students, middle school students, and grade school students.
Right, even in some cases, grade school students. This is being facilitated by the money that's available from the government, grants, primarily because of the fear of the Soviet menace and the need to bulk up in technical fields. It creates a situation where games can start to be created. And there are some games in the late 1960s and early 1970s that are created that are very influential games that continue to be around on microcomputers, games that persist for 15 years, 20 years, getting shared around everywhere and becoming true classics. And the reasons for that are both the time-sharing networks and then the gradual spread of these programs through different mediums, even outside of time-sharing, that allow them to spread across the country, all under this kind of lingua franca of BASIC that can be understood by all of these different computer systems, and which Kamini and Kurtz have made available free to whoever wants it. Because again, they're just all about spreading the love. They want everyone to be using computers. And so now that we've kind of explained how these time-sharing networks work and how these time-sharing networks got going, next time we can turn our attention to some of these very classic games that were being made on these systems and then discuss the methods through which they left individual time-sharing networks and literally spread across the entire country and even the entire world.
Sounds good. We'll pick up the hunt and spread of game next time on They Create Worlds. Check out our show notes at podcast.theycreateworlds.com, where we have links to some of the things that we discussed in this and other episodes. You can check out Alex's video game history blog at videogamehistorian.wordpress.com. Alex's forthcoming book will be released through CRC Press. Email us at feedback@theycreateworlds.com. Our Twitter is TCW Podcast. Please consider supporting us on Patreon at patreon.com/theycreateworlds. Intro music is Airplane Mode by Josh Woodward, found at joshwoodward.com/song/airplane mode, used under a Creative Commons Attribution License. Outro music is Bacterial Love by Roll of Music, found at freemusicarchive.org, used under a Creative Commons Attribution License.